Yes, wonderful. It's a pleasure to be here. Can you guys hear me now? Yeah, okay. So as I'm opening my water, I'll just put this here. Does anyone know why this is in my slide deck? Or what's going on? Is there anyone from Paris here?
This is not your slide deck?
No, it is my slide deck. Sorry, that was, okay, the talk's already going badly. The first slide is misunderstood. Okay, so this is actually just installation art. So it's like a gallery in Paris. The guy's looking for the needle in the haystack, and they issued a warning saying that it might take longer than anticipated. So why is this here? Because I'm going to tell you about my recently sort of developing viewpoint on how machine learning might contribute to protein design and protein engineering. So this is actually a relatively new area for me. We just started it when I moved to UC Berkeley around 2 years ago. And so it's fun to kind of give my viewpoint and then get feedback and keep going from there. So, but fundamentally, a protein is, of course, like a sequence from the alphabet of amino acids, and you're looking through this massive combinatorial space for the protein that you hope satisfies whatever it is you need. And so on the surface, it is just this massive, massive search, which is sort of like combinatorial optimization. But as I go through the slide deck, I'll convince you that it's actually even somehow maybe harder than that. And so why do we want to do these things? I don't know exactly the background in the room, but probably many of you have heard of these different use cases for proteins. So GFP is, of course, a very commonly used protein to just tag things both in big pharma and in labs. When starting this work, I learned from a colleague of mine at Berkeley about this protein rubisco, which is the most common protein on the planet and is involved in carbon fixation. And it turns out if you could modify it in certain ways for certain properties that are intention, this would have a great impact on agriculture and on the world in general. And of course, we have antibodies which act as drugs. One of my collaborations is on designing the AAV virus for gene therapy. And in my previous work, I actually worked a bit on some predictive models for CRISPR-Cas9. I did not work on protein engineering there, but of course people are also trying to, say, change the Cas9 protein, which does the cutting to make it, say, more specific and things like this. So I think it's probably clear to everyone in this room that it's very valuable to be able to change proteins to behave as we would like. And so that's, I'm going to present to you my viewpoint on that. And just, this is going to be the only slide in the deck about molecules, and the reason it's here is I was not intentionally going into this area, but as I started to give talks on this topic, I had some chemists approach me and said, the stuff you're doing I think is sort of equally applicable in chemistry, and so now some of my collaborations are with organic synthetic chemists and people doing a small molecule for drug design. And this is actually a much harder problem in some sense because instead of a linear sequence of amino acids, you have, of course, this sort of 3D topology and electron density clouds. And so the sort of fundamental problem of just how to represent this for machine learning is kind of an open and unsolved problem. Whereas, at least for proteins, we know that we can use the alphabet in sort of standard machine learning algorithms. Okay, so why is protein design difficult? So again, this is sort of like a massive combinatorial design. So even for very short proteins, we quickly get to the number of atoms in the universe. So even if you're DeepMind with lots and lots of compute, there's no way you can even come close to enumerating through all of these and picking the one you want. And so in some sense, fundamentally, this is right about like moving through, getting this needle in this haystack, moving through this really massive space. And that's what this talk is going to be, is how can we use machine learning to move more effectively through that space? So how is it done now? So it's not really done with much computation at present. The sort of really mainstream way to do this is a wet lab-based technique called directed evolution, which you probably know won the Nobel Prize in Chemistry in 2018. And it's this sort of very simple to think about technique, which is unbelievably powerful. So what do? You start with some parent protein that has the seeds of the property you care about. Let's just think of one property. It's tricky to do this for more than one property when you do it in the wet lab like this. And what you do is you induce a diversification step such that this one parent goes into a pool, becomes a pool of related variants. Maybe you say like throw X-rays at it or do some sort of mutagenesis. But the thing to keep in mind is the variation that is induced here is random, right? So it's happening at random places in the genome, a random change from an A to a T. Typically, you can impose some amount of structure, but at a broad level, it's a random stochastic process of diversification. And then key to being able to use directed evolution is to have some way to measure what you care about in the lab. So for something like fluorescence, this is obviously very easy. You can just measure fluorescence. You get to things like binding and so forth, then you need to have be very creative about how you're going to get at least a proxy to the thing you care about. But if you have that, then you can do directed evolution. And so you measure what you care about, and you select, say, something like the top 10% of the pool to get the things that are closer to what you want them to be, and then you cycle through, right? So this is very obviously much like evolution. It's directed because you're imposing your own fitness function based on the property that you're trying to select for. And so what I want to tell you about is how can we think about this as a computer scientist? And given that we're thinking about it this way, is there an opportunity here to perhaps do better or to act synergistically with the way people do it? So I don't think we're going to sort of take over from this, but the question is like, what can we bring to this that might make it better still? And so in this talk, what I'm going to talk about is I'm going to assume that the data we have is like frozen. I'm not acquiring new data. And the game is to say, I'm going to give my wet lab collaborator like let's say 5, he'll tell me a budget, some number of sequences, and those are the ones that he or she is going to try, and then that's like we win the lottery or we don't. So this is not a design of experiments, although what I'm going to tell you about here can sort of readily be tweaked to also do data acquisition. I'm just not going to talk about it. Okay, so if this is what directed evolution does, so what's the first place you might think about deploying some machine learning here? So we typically think of machine learning in the predictive modeling sense, which is actually not a great passion of mine, but indeed we are going to do this. We're going to replace the assay step instead of doing a wet lab, we're going to assume we have a predictive model. This is not actually my area of interest, but we need it. So with some collaborators, we'll build our own model, but if other people have already sort of domain-specific predictive models, we're quite happy to plug and play, and we would like the method I'm going to tell you about to, in particular, be able to plug and play with different predictive models. And so we want to be able to absorb quite general predictive models. And for me, the more interesting thing is to say, what kind of a search is directed evolution doing through this large combinatorial space? So from a computer scientist point of view, it's doing a greedy random search, right? So it's random because of this diversification step, which is somehow, it's inducing variance, but without any adherence to like maybe the manifold that proteins lie on or any sort of lower dimensional information or correlation among the points on the protein. So it's just random. And then the second thing is that it's greedy because we just sort of always take the top 10, we just truncate and throw the others out and keep going. And if you think about large combinatorial spaces and optimization, you know that a random greedy procedure is likely to just go very quickly to a bad local optimum. In this case, it's clear that it's not bad because it got the Nobel Prize and people can actually do a lot. But the question is, could we get to better parts still by moving through that space better? Or might we get to maybe similar places but somehow more quickly, saving rounds of directed evolution? And so in cases where you might be doing directed evolution with monkeys, and so just saving a few rounds can actually be dramatically helpful. So, okay, so I often get this question of, well, you have to model structure. In fact, I got into an interesting discussion this morning about this. And so I'm actually agnostic to whether we can predict the structure or not. If the properties that we care about are best predicted through structure, then great. As that gets solved, then we can leverage that. But in general, I think there's going to be a trend, right, to go from sequence straight to property. And we're starting to see this emerge. Whether you believe this or not, like, I don't care. I'm agnostic. And so we'll just take whatever works best, and I don't want to get distracted from this for the purposes of this talk. I'm just going to assume that there is this predictive model that's good enough, and we can ask what is good enough, and that's a bit hard to get your hands around, but I'll try to give you some idea of how we think about it. Okay, so we're going to start off with some predictive model that someone's given us. It could be from sort of physics-based approximations, or it could be just a neural network as I've displayed here. But the idea is that someone has already set these knobs. We're going to set the properties we care about. Maybe like we want to maximize one, minimize another, have another one above some threshold. For the purposes of this discussion, I'm just going to talk about maximizing one property because it's easier for me to talk about. But I think one can generalize from that fairly easily, although not that easily. Okay, and so the game is that to set these things and basically back out of the model what sequence here. So X1, X2, these are like amino acid sequences. How can I get that? And so again, when you look at it just on the surface, this looks like combinatorial optimization, right? I have some function and I need to find these discrete sequences to adhere to the property that I would like. And so I'm gonna like flip it on its head, as I just said. But one thing that is often overlooked in modern day machine learning is the uncertainty on predictions. And you can imagine in this case, when I'm trying to kind of back out of the model, that the uncertainty is going to be very important. And in fact, one of the open problems in deep neural networks right now is that uncertainty is actually not well calibrated. And we're not necessarily using neural networks, but this is a property that we're going to care a lot about and want to incorporate. And so already, just by virtue of that, this is not strictly a standard combinatorial optimization problem. Okay, so just to make sure the problem is crisp, the problem we're thinking of, which is my biased view, because it's what we're working on, is we want, given the ability of some model to predict from what I call the design space, so that could be a nucleotide sequence, amino acid sequence, to some property of interest, and we're gonna call that like our oracle model. We want a method that tells us what sequences to choose to, say, maximize that particular thing. And we may wanna add some constraints here. So we might say that we want actually very specific amino acids, in which case in some sense we're doing codon optimization, or we may say that we want a large part of the secondary structure to remain the same and only allow a small part of it to change. In any case, we want to be able to layer in constraints that are appropriate for the problem at hand. And the other thing we want is we are going to say that this model that someone gives us, it can just be like a black box model in the sense that we don't need to be able to compute gradients on it or anything like this. And in fact, gradients aren't super helpful here because we're trying to optimize something with respect to discrete sequences, and so there's not much gradient information there in any case. Okay, so basically the approach we took in the beginning, and I'll tell you a lot about this approach and what happens, and then sort of a tack on at the end is like what's actually wrong with this approach, but I think this builds up nicely. So we want this sort of black box oracle. We want to account for uncertainty of the oracle, and that's probably going to be heteroscedastic noise, right? It's because different parts of the space, it will look different. And in fact, we also want to be able to provide a set of good candidates, not just one. So you can imagine if we could follow a gradient or something with like one particle, that would just give us one protein, but we want like a diverse set of candidates. So the solution sort of algorithmically here that we're going to use is going to be based on, or something that we and some other people call model-based optimization. And if you haven't seen it at first, it's kind of weird, but in fact, it's quite intuitive once it clicks in your head. So normally if I think about optimization, I might think this is maybe this oracle for some property, and X is the protein, and I'm trying to find the protein that maximizes this property, like let's say fluorescence. So in model-based optimization, instead of searching over the protein itself, I'm going to search over a distribution over proteins that are parameterized by theta. And so like you can imagine if X was actually real valued, this might be a Gaussian. And so this Gaussian is going to somehow be in some, it has a center in the space and a variance. And then for each of these, I can take the expectation of the property I care about. And if this has a high enough capacity, if it's a rich enough representational model, it can put a point mass on one X that maximizes f of X. And if it has that high enough capacity, then these are sort of trivially equivalent. Doesn't mean we can trivially solve it, just means they're trivially equivalent. And so that's the game here. And what's really nice about it is I've introduced the language of probability into an optimization problem, and that's going to be a nice language to have for me to work with, and we'll get to that. But so just roughly intuitively, the way it's going to work, right, is this sort of, we call this like our search model, and it's going to get updated in an iterative manner. And so at some point, we just initialize it somewhere in the space of proteins, and then we're going to sort of draw samples from it. We're going to evaluate them according to this sort of oracle predictive model, the property we care about, and then we're going to adjust the parameters of this sort of spotlight in the protein space and move it in an iterative manner until it arrives at a part of the space where we can just sample sequences from it. So that's what we're trying to do. Right, and so this can sort of sample broad areas of the space. It's sort of aware of more than just a single point. But I think the main point here is that it actually uses tools. We can bring in tools from probabilistic modeling and use the language of probability in the optimization, which will turn out to be actually, I think, one of the key ideas in this field. Okay, so our aim now is to solve this thing where this now is, say, this is a predictive model for the set of, for proteins that have like higher than some fluorescence level, some minimum fluorescence that we want. Maybe it's the maximum value, and this is a distribution over proteins. And so here, the details, I mean, at least the way we're thinking about it now, a lot of things I'm agnostic to at this general level. Once we dive down into particular collaborations, we're gonna have to think very carefully about these things. So it's not to say they don't matter, it's just that I'm not gonna tell you any insights about them because we haven't got that far yet. So we're using a variational autoencoder here, but it could be an HMM. This could be a mixture of multinomials, anything like this. And right, this is this sort of oracle predictive model, say a neural network, and we're gonna also need its uncertainty. And S is the sort of desired set of properties. So it's a little weird to explain, but let's say if you were trying to maximize fluorescence, it would be this weird sense of all fluorescence levels higher than or equal to the max, which is a bit weird to think of, but just for the sort of notation to work out. So I'm not going to go through the development of the algorithm that we arrive at from this, but so what I've just told you is we're going to use this model-based optimization scheme, and what emerges from it is a probability distribution over proteins from which we can sample 1, 2, 5, or however many we want. And this is going to be an iterative algorithm. The details are in the paper and I can talk offline, but ultimately what it looks like is at every step, you take a bunch of samples from the current version of this search model, and then you basically weight them according to your oracle model and its uncertainty, and then you end up with a weighted likelihood estimate for that search model itself, and that moves it, and then it just keeps moving. So I don't want to go into all the details, that's just the intuition here. And what's nice is there are some other papers out there proposing algorithms, but they just kind of pull them out of nowhere. And I think one nice thing about this is it's sort of written sort of from first principles. Even though it's technically like an NP-complete problem, we can't solve it, at least you can see where it came from and what's going on. So, and what's kind of cool is we were not trying to design an algorithm that looked or mimicked directed evolution, but in fact the algorithm does have a very nice analogy to directed evolution. And so I just want to paint that picture here with the pseudocode rather than getting bogged down in the math. So this is, the sort of algorithm requires this oracle, this is its mean, this is its cumulative density function, which accounts for the uncertainty. So we need these things, of course, and at the moment we're not updating these, although you can imagine updating these in particular ways might be helpful, which is something we're exploring. But for now they're fixed. And then we need a generative model, like a variational autoencoder or something that takes weighted samples, and given those weighted samples, it trains itself, and now we have this trained model. And then we can, if we so choose, initialize this algorithm as you would initialize with one or several proteins that you think might be a good start, but you don't have to. Of course, if you don't initialize it, you may not get to as good of a place, or it might take you longer. Okay, so given that stuff, then you take if it was initialized, you take those initial proteins, you weight them all to be the same. If it wasn't, you just develop some randomly initialized set of proteins. And then, much like directed evolution, we're gonna follow a loop. And so now, instead of this sort of physical diversification step, we're going to sample from the generative model that's trained on the current set of points. And so the kind of key intuition here of why this, I'm going to try and highlight why it might be better than directed evolution, is that this generative model, if we've done a good job, should somehow understand the space of proteins, should understand which points are correlated with each other. And so when it's making sort of a random move, it should be doing it in a way that somehow is adherent to the space and therefore moves more efficiently through the space, as opposed to these sort of more random operators that happen in a physical system. Next, instead of measuring things, we're going to score them with this predictive oracle model, and we're going to account for the uncertainty. So I'm not going to go to the details, but now each one gets a weight. And so now I've changed what was just sort of totally a random diversification step into something that makes use of a generative model, which should understand something about protein space. And I've changed what was greedy to, it's still kind of greedy, but more softly greedy and accounting for uncertainty. And so the hope is with these two things combined that we can move through the space more efficiently. And as I said, it's not like we just wrote this down. This comes from sort of a derivation of an algorithm. Right, and then we're going to repeat here. And so what's kind of interesting is who here's heard of genetic algorithms? Okay, so when I was a PhD student, this is like a dirty word, and like if I said it, I would have been kicked out of my PhD program. And so I kind of always vowed, not apologies to anyone. They're useful, they make progress, so don't take that the wrong way. But these, interestingly, so when we developed this, we didn't know, but it turns out we sort of independently developed an algorithm related to a whole class of algorithms called estimation of distribution algorithms, which are kind of the modern day equivalent version of genetic algorithms. And they're a bit more rationally motivated in the sense that instead of these sort of random mutations and crossover operations that are not adherent to the space in which you're moving around, you do generate from a generative model. And so this should be nicer and it should work better, and it does in fact seem to work better. But I would argue that in fact we've derived this in a much cleaner way, I think, than has been in the literature. And in fact, we've shown now, I'm not going to go into more details, but we have a preprint out that shows that these EDAs can actually be written as Monte Carlo expectation maximization, which was not previously known. And so I think that brings a nice coherence to this area of optimization. And also something else is where I would never work in is reinforcement learning, maybe just because it's like even more hyped up than machine learning in general. But it turns out that the underlying techniques here have a direct mapping to some of the techniques used in reinforcement learning where you have stochastic policies. And in fact, some of my most synergistic productive conversations have been with my reinforcement learning colleagues, which is pretty interesting. And it's actually, this is also tied to image generation literature. And so this is a very neat space because I've never worked in something where we kind of came up with an algorithm and it sort of touched so many places of research that we didn't know about in advance. Okay, so great. I told you about this algorithm. It has this like cute analogy to directed evolution. Is this of any use? So we came up with this and we started to see if it would work. And it looked like it actually, something was terribly wrong. So I'm just looking at time. Is it true that I have 5 minutes left, just to check? Did we? Okay. How much? Just so 10? Okay. We'll adjust accordingly. Okay, does anyone have some idea of what's going to go wrong if I try to deploy this in practice?
Yeah, you're going to get stuck in some sequence that doesn't work.
Yeah, why?
Because the space is huge.
No, I don't think so. But okay, just for those who didn't hear, he said, we're going to get stuck with some sequence that doesn't work. And I said, yes. And then I said, why? And maybe we can have a discussion about it. But so the reason is, in my mind, is that this oracle, even though I said we're accounting for uncertainty, we've assumed that the uncertainty is correct. And this is actually a preposterous assumption, even though everyone in Bayesian optimization makes the same assumption. In fact, we're going to try and touch that field with these ideas soon as well. So, you think I have captured the uncertainty, but to the extent that a model is biased, like imagine I train it in some region of data space, and now I go further and further away from that data by some definition that I'm not going to say because it's actually a difficult problem. But as I get, let's say, further and further away, the point prediction is going to get worse and worse. The model is going to become arbitrarily biased. And to the extent that a model is arbitrarily biased, then it's arbitrarily uncalibrated in terms of its uncertainty. And so the fact that I say I can make use of the uncertainty is true, but that uncertainty is basically going to be completely wrong at some point. And so at some point, I'm going to get to a part of, I'm going to call this predictive model, and it's just nonsense. And so I'm going to be optimizing for this nonsense model. Okay, so this is kind of an impossible problem, like most real problems. So what can we do? I'll tell you how we think about it. But just to drive the point home, if that predictive model, that oracle, is like a deep neural network, which I think it will be in many cases because these can provide state-of-the-art performance, these have these sort of black holes, right, that no one understands. That, like, I call them black holes. I guess people think of them as like adversarial examples. So, you can train a model that gets state-of-the-art performance in classifying like stop signs, let's say traffic signs, and like this one would normally be classified as a stop sign, but as you may know, you can add this sort of tiny amount of human imperceptible noise using just a tiny little gradient calculation to that image so that it looks like exactly the same, but now it gets misclassified as a yield sign. So what is this telling you, right? This is telling you that these models, even though they have state-of-the-art performance, that they actually, in some sense, they're also complete nonsense, right? And so this is like people keep chasing this, like, okay, I can make it adversarially robust by this and this, but at the end of the day, like, there's still these weird holes in there. And just to drive the point home, actually, another example, like in this case, is a model that thinks that everything with a yellow box has greater than 50% chance of being an airplane. Okay, so right now I'm just demonstrating these models are kind of funky and weird and don't understand anything. But what's going to happen if I have a model like that and I do what I've described that I want to do? So it turns out people have sort of done this for images. They say, I trained a classifier on bananas and animals, a whole bunch of stuff, and now I want to know what the neural network thinks a banana is. So I'm going to do kind of what I described to you before, is I'm going to set the desired property to be banana. So this one, y2 is banana, it gets a 1, everything else gets a 0. And then what they do is they use sort of gradient backpropagation to find a single input that maximizes the banana. And so when you do that, you start with a random image here, and you get to this kind of a thing. So obviously, if this is me designing proteins, like that's going to be a nonsense protein precisely because of this weirdness about state-of-the-art deep neural networks. And so this is exactly what happens. And in fact, I think it happens even with simpler models as well. But the more sort of high capacity, large number of parameters, the more likely this is going to happen. So now we want to revisit what we've been doing. We're going to stick with the same overall framework. But we want to account for the fact that this oracle may be arbitrarily biased and have just totally, the uncertainty might be totally off. And so we're not magicians. We can't completely fix this because that's kind of crazy. So what kind of practical thing can we do that maybe is like a nice trade-off to keep us in a sane part of the space while still allowing us to make progress? So the way we're going to try and get at this is in one of two ways, but they both share the same theme, is somehow I want to model the space of proteins that I think is reasonable. And so like that's a bit in the eye of the beholder, but how might we go about this? So in the case where I have access to the data that this oracle was trained on, maybe I know it was trained on this part of the space, then I can just take those X's, those protein sequences or molecules, and build somewhat sort of a density model over them. And if that's reasonable, then I'm going to make use of this to try and rein me in. And I don't know if I'll have time to explain how it comes in exactly, but we may not have access to those data. So in this case, I'm just saying, take a look at where the model was trained and roughly in a soft way, trust it near there, but still allow yourself to go a bit further away to make some progress. Alternatively, if this is some physics-based model and I don't entirely know, like it wasn't trained somewhere or I don't have access to where it was trained, I can just think of this more as like being a Bayesian of like, what is some density that makes sense for me to inject prior knowledge here? And so you could imagine perhaps just downloading all proteins known to fold and just modeling the density over those and somehow reining in the search over all your proteins by this. And again, like depending on the exact domain and problem we're trying to solve, we may do this differently. And I think there's room for creativity to be had here. But roughly speaking, this actually isn't, I'm not going to go through all the details, but this is the algorithm, the iterative update I showed you before. And just to show you that it's sort of intuitively pleasing, what emerges from this is we get the same update, but it gets modulated by a factor. And that factor here is basically how much does that new protein sequence that I've sampled, what's its ratio of how much it belongs according to that prior density, if you will, as opposed to the new current density. And so it gets mitigated if it gets kind of too far away from where I say I trust it. And it downweights it in this update, and it has less influence on where that sort of spotlight moving through the space goes. Okay, so that's sort of part one and part two. It's an algorithmic framework, and this is exactly why the language of probability is useful, because now we can start to bring in how we model where we trust the space and things like this. Okay, so one really, really hard thing here is how you actually, now we have this nice algorithm. How do I convince myself that we've done anything, right? Because the whole point here is that I'm not trusting a predictive model relative to ground truth. So I cannot even really, in most of machine learning, we just hold out some samples, we train, and then we say, how well does it work on these? Like I cannot do that here. So it's really, really tricky. And in fact, what people are doing is they're publishing papers where they just assume the oracle is correct, and then the game is how good am I according to my oracle, that's just optimization, right? Like you may as well just go into optimization and take the best stuff there. But this is, I think this issue of trustworthiness of that oracle completely dominates whether this will work or not. And you can probably use almost any optimization scheme otherwise. Maybe it takes you a bit longer and does a bit worse. But so what we're gonna do is we've done a number of things, but just to give you an example of how we try to test it in silico before going to the lab, this is some GFP data. So this is the fluorescence. And we take all the proteins which lie in the, I think, bottom 80th. I don't know, I'm actually 20th percentile, whatever. We take some bottom amount of the fluorescent proteins and we don't let it see the top ones. And sorry, I back up. jet lag screwing my brain up a bit. We take all of the data and we train what we call a ground truth model, because we don't have a ground truth model, but we need to pretend to have one. And we just, in this case, we use a GP function and we take the mean, and that is our ground truth. And so that's, for us, for this experiment, is like the physical reality. Then we truncate those points and we train an oracle model with only like the small ones, so to simulate the situation we would be in where we'd like to get here. And then we can perform experiments with this. And the idea is, if you've only trained on these, like this is a sort of illustrative example, is the blue is what the, in X space, let's say single dimension, blue here is what the ground truth looks like in fluorescence. And the model you build, because it's only seen these points here, actually keeps going up here. And so what's going to happen is, if you apply sort of the more naive method, it's just going to keep going way out to some crazy part of the space. And the idea is that we're going to rein it in by telling it basically what we think is more plausible. And so if you do this kind of experiment, we can run different algorithms and show that this one behaves well. But of course, this is simulation, so it only tells you so much. It just says sort of the way we're thinking can have some utility here. But at the end of the day, we need to go into a lab and work collaboratively with people to actually see if it's working, how we might change it, if we have any errors in our thinking. And so I'm not going to, because of that, I'm not going to dwell too much on highlighting, some results in a paper. But and I'll just say, rather, what I think is more important than the results is to say, well, we're actually taking this very seriously, and we're starting up a bunch of collaborations. Some of these are more active than others, but so we're looking at protein stability and binding with Eric Clavens, whose lab is next to the Baker lab. And so some of these properties right now kind of use Rosetta and to model at least part way. And so it's a nice testing ground, because we know there's an alternative way to kind of do things, but we would of course like to deploy this on properties that cannot be handled by Rosetta. And so one example is David Schaefer does this gene delivery system into the eye and all kinds of crazy stuff. He has stuff in like FDA approval, and so right now we're trying to improve the packaging success of the libraries to take in the sort of payload. We just started improving some, or trying to modify some enzymes to manufacture hydrogen peroxide at scale and cheaply. And we're playing a bit in the chemistry space with this consortium, which is EECS, the national labs, doing small molecule design, and they have a pilot project that we're involved with, and some organic synthetic reactions with Caltech. So it's very early days, and I'm just kind of telling you the adventure that we've started 2 years ago, and we're always looking for feedback and opportunities to collaborate and corrections in how we may be thinking about things. So I have some open challenges on the next slides, but I think because we're over time, I'm going to just stop and thank David. So David was my very first student when I first started at UC Berkeley, and he and I have sort of been driving this. And these are two newer students who helped with the EM paper. Okay, I'll stop there. Thank you.